Alright, so next we will talk about how to use the autoencoder as a general architecture for many of the basic models. If you still remember in the previous pages when we introduced autoencoder architecture, we mentioned we can use this MLP as an encoder and decoder, right, for us. It can help us compress the input into embeddings and also reconstruct the inputs again. Right. In this way, we can do the learning of the autoencoder, to learn both the MLP in the encoder and the decoders, right, by minimizing loss function we define here. So this is a general way we show the model architecture of the autoencoder. Actually, we can use different models to define the encoder and decoder. Besides MLP, we can also use many other deep learning models to help us to define them. For example, we can use this RNN, right, recurrent neural nets. Even though we haven't introduced this RNN yet, but I can show you some examples how to use RNN for defining encoder and decoders in the autoencoder model. In this page, we show you an autoencoder with this RNN as an encoder and decoder. We can use this autoencoder for the speech recognition. Given the speech input, we can try to generate the text contents inside this speech, right, which will be called a speech recognition task. So given the audio input, the audio segment, so via some models, we can generate the learning target, which will be the text or words of this input audio, right? So we can do this kind of task with autoencoder model. So the architecture will be very similar. Given the audio inputs, we can represent it as some vectors, right? We can represent this audio as a vector. It is a time series vector or some sequence vectors, right? And then we can feed this vector to an encoder. This encoder will do what? This encoder will embed this input into a vector, right? However, here, since we are starting the audio segment, it will be very different from the conventional feature vector input. We have to utilize some specific model as an encoder for us, right? Here we can use this recurrent neural net, or RNN for short, as an encoder. This RNN is a sequential model. Given multiple inputs, it can accept its multiple inputs into a sequential manner, right? We have x1 until xt. And this representation we learn for the x1 will also be serving as the input for x2 as well for this neuron, and similar for the remaining. So it is a sequential model. There will be some patterns or sequential patterns among the neurons. We will discuss this RNN in the following lectures later. So you can see we can use this RNN as an encoder. This RNN will serve as an encoder to compress this input into one embedding vector, right, like this one. And we can embed this whole audio segment into one vector. And this embedding vector will be serving as the bottleneck, as we showed before, and also serving as the input for the decoder as well, right? So we provide this embedding vector as input for the decoder. And there are also different ways to define the decoder, like the recurrent neural nets, right? We can also utilize another recurrent neural net as a decoder. So you can see this decoder will also be a sequential model. We have multiple neurons, right? So based on this vector representation, Z embedding vector, as well as decoder, we can utilize it to reconstruct this text contents inside the audio, right? So for example, we can have this Y1 until YT as the output. So you can see in this autoencoder model, we have both RNN as an encoder and a decoder, right? They are both sequential models. And the embedding for one of the neurons or the final neuron of the encoder will be the bottleneck, and it will be serving as input for the decoder actually. So you can see compared with this original autoencoder, this one actually the architecture is the same. However, the main difference relies in how we define the encoder and decoder showing here, right? And how we do the processing for the inputs and outputs. However, the general architecture is the same. We still have the inputs, encoder, decoder, outputs, right? This is one way we can use this autoencoder to help us to do the speech recognition. However, here when we are learning this model, we don't need to minimize the difference between this one versus this one anymore, right? We just need to ensure this output will be, compared with ground truth. Normally, given all the inputs, we have the ground truth, right? We want to minimize the loss function for the learning targets versus the ground truth to define loss function. And in this way, we can learn the encoder and decoder, right? In this task. Besides speech recognition, we can also apply the autoencoder into some other tasks like language translation, right? So normally, in the real world, we have so many different languages like English, French, Chinese, Japanese, and many other languages. You can see, right? And when we try to translate one language from another language, how can we do this? When we do the translation with deep learning models, we also need to do the embeddings of the inputs, right? The formula given the inputs in one language, like in English, I'm a person. I can give this sequence of text as inputs into an autoencoder model. Inside the autoencoder model, we can have the encoder to be one RNN, right? So this RNN will receive this sequential inputs, right? And inside it, then we can embed it into an embedding vector. So in this RNN, it will capture the sequential patterns from text inputs and then the representation, then the embeddings, right? And then we can feed this embedding as inputs for the decoder as well. And in this decoder, it will be doing what? It will be doing a reconstruction of the target, right? We can do the translation, with this decoder instead. Here we encode this into a vector, and then here we do the decoder to reconstruct, from the embedding vector into some text, right, instead. Then we can translate this language from English to another language instead. I don't know this language, probably you recognize this one, right? Either French or Germany, I don't know, right? So, this way we can do a translation with autoencoder architecture as well. So besides this speech recognition as well as language translation, we can also do many other tasks like for the image processing, anomaly detection, recommender system, information retrieval as well with autoencoder architecture. So it provides a very general architecture for us to study many of the problems. So given the input, we try to compress it into a vector, embedding vector. Then we can reconstruct it, right? Depending on the task, we can either learn it in an unsupervised way as like this, or we can learn it according to some loss function. We define the learning targets, right? As shown here and shown here. So here we show two models utilize RNN as an encoder and decoder. Besides this, we can also use some other models as an encoder and decoder as well. Now here we show another example to do the image style transfer with autoencoder architecture. So formally given the image input, we can do some style transfer of the image for us, which can generate some new images. And this new image will have similar contents but with different styles. At the bottom, we show an example. Given an image of a dog, as shown here, right? And we may consider to change the style of the dog image into some painting styles. Now we show the style bank here. We want to convert the style of this image into this style instead, but still with the same contents. And on the right hand side, we show the desired outputs. We are still showing a painting about a dog. However, this painting style is very similar to the style we show here, right? In this way, it is called a style transfer of the images, right? The same contents, but with different styles. And you may wonder, how can we do this kind of task? It seems to be very fancy, right? And you may also wonder, how can we address this task? Actually, we can also, do this style transfer with this autoencoder architecture to help us. What does this mean? So formally given one image input, it will be a color image input, right? And then we can feed the image as input for an encoder. What is the encoder? Here we define a CNN model as an encoder for the architecture, right? Before we mentioned we can use MLP, we can use RNN as encoder and decoder. Here we can use the CNN. It means convolutional neural nets we will discuss later in the following lectures. It's a model proposed for handling images specifically. So we can define a CNN as an encoder here. It will embed this image into a feature representation or feature vector for us, right? So these embedding feature vectors can be serving as input for decoder. Because here we use convolutional neural nets, then we can use this deconvolutional neural nets as a decoder to help us to reconstruct the image instead from a feature vector representation, right? So this is the encoder, this is a decoder, this is a bottleneck. The learner embedding vectors. And then we can reconstruct a new image, generate the output, right? So if we are doing a simple image reconstruction, we can work in this way. However, if we are starting the image style transfer here, then we may consider to incorporate more information into this bottleneck embeddings, right? So this embedding we learn from the images. Then we may consider to incorporate this embedding vectors with some style information. We learn the style information from our style bank. which will also be some other images, right? From the style bank images, we can also get some vectors describing these styles, right? There are different ways to learn this style vector from the images. For example, we can also utilize another encoder here to embed in these style images, right? So we can integrate the style vector into the learning embedding vector for these images together. Then we can define a new embedding inputs for the decoder instead, right? So you can see, we have a conventional embeddings, then we can have this serving this one as an input for decoder, right, to reconstruct the original inputs. When we integrate this embeddings with some style information, we can also feed this one as an input to the decoder, right? And it can help us to generate different styles of this image again, according to the style we're feeding them, right, into 3 different styles as shown here. So then the question will be, how do we define the loss function? We have different ways to define loss function, right? One loss function will be we want to ensure this image input as well as this reconstruction to be as similar as possible, right? To ensure we can learn meaningful embeddings and also meaningful encoder and decoder here. Also, we want to ensure the style compared with style bank as well as the input to be similar as possible. We want to minimize the difference of the styles versus style bank, also minimize the contents versus the inputs as well, to ensure we can learn very useful styles and with the same contents. So this is another example we can show you about how to utilize autoencoder to do something more interesting than the reconstructions, right? We can do the style transfer, to add some styles to the image inputs and to generate some new style of the images. So you see, this autoencoder is a very general architecture inside by providing it with different kinds of encoder, decoder. It can serve in different functions. So here we can do the style transfer. We can do the translation. We can also do the speech recognition from the audio inputs, right? Besides them, we can also do many other interesting things, as later we will show you how to use autoencoder as a general architecture to help us. Alright, so these are the potential applications of autoencoders. Then next we can move to some more variants of autoencoders and how to utilize them to address many of the other challenging problems